Thanks, Andrew. Yeah, I think especially that second to last, Andrew's second to last slide really leads into this well about prioritizing sample requirements for EOVs. So I'm going to assume that EOVs have been chosen, and we need to decide how we're going to observe them. So from a practical point of view, prioritizing sampling involves identifying gaps in our knowledge. If we are designing a Southern Ocean observing system from Argo, how much are we already missing with respect to the other variables? And I'm talking about not just TNS, but I'm talking about SSH and biogeochemical variables. And so we pose the question, what is the mapping error of my SOOS? And the prioritization comes down to the reduction of the mapping error for all the EOVs. Okay, so I got some text slides here. Okay, so projecting observation information using covariances reveals the extent to which a measurement has reduced or has improved our knowledge and reduced our prior uncertainty. So if we know nothing about a region, we take one measurement, what are the scales that we now understand that region? And there's two problems to determine an optimal SOOS. And one is that we don't know the true spatiotemporal multivariate covariances. We can calculate them, but it's a large dimensional problem. We also have, once you know those covariances, you still need to map them, and that's another large problem. So the simplest, it's right here. The simplest mapping is single variable objective mapping using no temporal correlation information. When you add temporal correlation information or multivariate information, the problem gets significantly more difficult. There's a lot of dimensions, more complexity, and there are complex methods for dealing with this, especially with the time dimension, and those call on Kalman filter method or the 40 var method to give that space-time correlation information. So I'm going to walk through the first steps in determining multivariate mapping errors. I'm not going to address the time dimension. I'm not going to use a complex method. I'm just going to use EOFs to project mapping error. But this is a framework that we could use to, for example, when we have several ships heading to Heard Island, to figure out where their gaps are going to be. Should we send one ship in a certain different way? And I think that's something that SOOS can really contribute to in terms of coordinating these observing schemes. Because mapping is a big problem and computationally intensive, I'm only going to focus on the Amundsen-Bellinghausen C for this talk. It simplifies the talk a lot. So what I'm going to do is I have a model solution. I think it's 8 years, and I'm going to project that into EOF space, get 50 EOFs that represents the variability of temperature, salinity. I've chosen a couple of variables here: oxygen, nitrate, and pH, all at just 125 meters, and also SSH. So these would be my EOVs. And I'm going to say what sampling strategy will then maximize that information about those variables. Okay, so here's the domain. First, I will show the whole globe and just show what the RMS, or what the standard deviation of the signal looks for. I've already taken out the seasonal cycle and the trend, and you'll notice that these variables don't, especially in a circumpolar view, don't vary in the same way. Temperature and salinity, you really notice the subantarctic front, whereas nitrate, you notice the subantarctic front, but you also really notice the ice edge. Oxygen is just hugely variable in the polar gyres, and pH is kind of somewhat like nitrate, somewhat like oxygen. So all these variables vary in different ways. They don't project together, but they do have a lot of the same covariances. So now we're back to the Amundsen-Bellinghausen Sea. So here's the Antarctic Peninsula. And this is the standard deviation of the fields in this region. Here's SSH. You can see this is the polar front coming through. Temperature, standard deviation, salinity. Again, nitrate is different. It's going to vary primarily. The dominant mode of variability is right along the shelf. Oxygen at the ice edge, and pH is mostly at the ice edge too, where the seasonal ice melts and we get a lot of variance in oxygen. So when we project this into EOFs, multivariate EOFs, this is what the dominant mode of variability looks like. It explains 30% of the variance. And I should just reiterate, this is from a model solution. It's from a third of degree model solution, so it's relatively coarse. And that's actually kind of nice for mapping. We have smoother EOFs. You can think of these EOFs as projecting the correlation scales. So where does kind of the whole system vary together? And for example, for nitrate, we see this kind of a mode here of variance. And if I had a very high resolution model, that might be masked. But this is the EOF1. We can look at all the different EOFs, and they do get smaller and smaller in scale as you get to more detail. I'll go through the first couple. And again, they vary in different ways, but you do see similar patterns too, which implies when you see similar patterns that if I knew temperature really well here, I'd probably be able to say something about nitrate here. Now, we're doing this through EOFs, through regression analysis, and we're not doing this through something like an adjoint model. So when we have no variance, we can't say anything at all, and that is one shortcoming of the method. And stop me if anyone has any questions, please. Okay, so sea surface height. Now when we get to EOF3, we see there's a big mode, kind of a basin mode of EOF3. With regard to SSH and pH. And EOF4, this is the last one I'm going to show, we're starting to get into even smaller scales, especially out near the polar front. So what we do, and here's the math slide. If you have EOFs, that's your H, and you know the expansion coefficient, that's your X, you can map the state of the model. So I can reproduce the state of the model because I know what H and X are. That's what I decomposed. Now the real ocean state is different, but I'm going to assume it has the same kind of statistics, so I have the same H. And now I need to say what is the actual X of the real ocean. Here, Y is the measurements. That's your observations. And so it's the same H, but it's only sampled in data state. It's only sampled where we measured. And then you can estimate the real expansion coefficients to get the real ocean state with this formula here, where R is the measurement error. This thing is kind of, battery's dying, but you have to follow me anyway. R is the measurement error, and P is the prior uncertainty. And so you see it's kind of 1 over R. And so if you have no measurements, P tilde just becomes P. You haven't learned anything. You have the same state you started with, the same uncertainty map you started with. But as you have more and more observations and you project them onto the map, you have you reduce your uncertainty, your a priori uncertainty. And the mapping error is formally just given by H, which maps back to the model state or the real space state times this P tilde. And H transpose again. So basically, we just make maps of this. We say, all right, well, here's our measurements. Here's our observing system, that R. And what is our mapping error if this is our observing system? So for this example, I assume P is just the original model state. If we have no observations, we just have the model state. We know the original model state. If we have a measurement, I say that's going to have a very small error. So we know the system where there's that measurement. And then we can say how much is the mapping error reduced by adding more data. What if we had observations every 1 degree or every 5 degrees? What if we had observations of temperature and salinity versus just temperature? And prioritization is a balance between reducing the mapping error and practicality. So you can make cost benefit with this. You can quantify everything. So I'm going to go through a couple examples of what if we had measurements on a 5-degree grid. And this is what if you just had SSH measurements. When you see values of 1, that means you haven't improved anything. The error is exactly what you started with. You know nothing about the system. When you see values of 0, you've measured it, basically. And most things are usually in between. And I don't know if you're going to be able to see it. The definition is not great, but you see a little white dot there, white dot there. Those are my measurements. It's every 5 degrees, and it goes right along the coast. I can show you these plots again later if you want to see them on the screen. But here, so we measured SSH in this example, and you see that now I've actually learned a lot about temperature. I've completely reduced my temperature at 125 meters by measuring SSH. Salinity too, although there's some edge, there's some lack of information at the edge of my sampling domain. Nitrate we constrain as well, but oxygen we don't. pH we don't do well either, and we know there's a couple places where we've learned nothing about pH. Yes.
Is there an implicit spatial scale in the factor of 1?
So the spatial scales come from the EOFs. So you might imagine that if you had this is EOF 1, you might imagine if you had a measurement here, it would say, I know everything about this spot right here. And that might also correlate to this spot here through the EOFs. And so the scale, so you might imagine if you had a measurement here, it doesn't give you much value because it's a very small scale as opposed to this large region. So you can kind of figure out where you should sample just by looking at the EOFs, which is a lot cheaper than inverting to get the mapping error. And you can see that through here. We're just projecting the measurement through the EOFs. Okay. So this is how we figure out what altimetry gives us. And then we can say, well, what if we don't have any SSH because there's sea ice, but we can measure temperature. And so we say, all right, here's the temperature observations at 5 degrees. And you see that, well, now we've lost all our SSH information. It doesn't go the other way. But it does keep the uncertainty in temperature down. We've also learned a lot about nitrate. And unlike SSH, it constrains oxygen. It constrains pH pretty well too. There's some in the polar front, it just stops kind of constraining salinity up there in the corner. And go through and with salinity, you also completely constrain temperature, a lot of these other variables too, and you do a little bit better with SSH too. So according to the variance in this model, you're much better off observing salinity than temperature. You really get a lot out of it. Okay, nitrate is some interesting information here too. And again, these are just examples. We can put in any measurement structure and project them and figure out how nitrate is going to do things. And if we put nitrate and oxygen, what would happen? So you can get the relative importance and start prioritizing your sampling. This one is for oxygen. So you might say, all right, I really want to know pH at the coast. Which measurement should I make? And it may not be that you need to measure pH at the coast. You might be able to do this through measuring other variables. Especially, well, some coastal regions, you see oxygen, by just having an oxygen measurement along the coast, you start to constrain pH at the coast. Of course, you have to trust this model. The variance in this model is the correct variance. Okay, this is the last one for the 5-degree grid, and this is pH. And even though we have measurements of pH here, we're still a lot of regions, the scales are really short, so in pH at the coast. And you can see kind of some places where there's no information projected. Okay, so that's all 5 degrees, and then you can play other games, like what if I measure everything at 9 degrees, and all of a sudden we win. We get pretty much everything, except the polar front still has a lot of variability. That the edge of the, I know you probably can't see it, but the edge of the array just goes to here. It's this little box right here, and it doesn't project out into the polar front for these variables. Okay, so this is what I showed with SSH on a 5-degree grid, and you saw that when I measure SSH on a 5-degree grid, in this box, I don't know much about oxygen. But if I measure SSH on a 1-degree grid, if we think maybe 5 years or 10 years from now when we had laser altimetry and wide swath SAR altimetry, on a 1-degree grid, it completely constrains this model solution. There's very little that's left by just having SSH at all times on a 1-degree grid. So that's what I wanted to talk about today. It really is just a way to to project our information and kind of get at what Steve was asking, developing quantitative assessments for how much we know. But there's a problem. It's one big issue that it's unfortunate because we have enough trouble coming up with EOVs. You really need to, it's not enough to just say, oh, we need nutrients or we need oxygen. You need to quantify what accuracy you want, or you can't actually determine if is blue what you need, or is 0 or 0.5 or 1. We need to decide EOVs and EOV accuracy requirements. And this, you could think of this just as a location or maybe varying in space as well. So the summary and the way kind of I see the path forward for this is that one thing SOOS can do is provide kind of an observational system simulation experiments, these OSSEs, these basically projections of how much information we get out of a measurement. And for kind of traditionally, the way people think of OSSEs is you sample a model state, so you observe the model state, and because it's a model state, truth is now known, and you utilize data assimilation, some method, it can just be what we did here, to produce, to try to reproduce the model state and quantify the ability to reproduce truth. By doing this with an ensemble of sampling strategies, you quantify which one is optimal. And this was Andrew's second to last slide, where he had the little line going through, and you can figure out if that strategy was optimal. So the simplest OSSE is if you had a state of one variable, and the data scheme was just objective mapping with isotropic covariance. The answer would be you want one measurement every decorrelation time and every decorrelation space. It's pretty simple to figure out what to do, but of course the real world has many variables, and these do inform each other. And so you really need to take into account how correlated temperature and oxygen are, and ecosystem variables as well. And these scales of correlation are very, very spatially dependent, temporally dependent. So it really calls on the need for a more complex data assimilation scheme like 40 bar, where you use the adjoint of the ocean model to get the true, or at least what the model physics claim are the multivariate covariances. And it's really nice because it doesn't depend on regression analysis. It just projects the measurement information through the model physics, but it's also very expensive. So if you actually wanted to do an ensemble of sampling strategies, like I just picked 7 here and it was quick to do, but with a complex scheme, it's just too expensive. So we have to figure out kind of what to do about that. But the first steps are just to probe these scales, make EOFs of different models, and figure out where our big gaps are and how successful our current observing system is. There are a lot of now objectively mapped products like Aviso maps and Argo maps. There are data assimilation reanalyses and real-time forecasts, and here's a list of some of them on this page. They only list the global ones, but it's a large list, and we can go through and do validation of those solutions and see how well we're doing now and where we're doing poorly. But at the very least, we want to extend the kind of multivariate analysis example given here, so that we can, when we're going to plan a couple ships in the same region, figure out where the gaps are going to be with that. So, yeah, as I said, full OSSEs are expensive, and also you do want to quantify things. You do want to know how much you know, and so you do want to have accuracy requirements. The adjoint sensitivity experiments give you the true correlation scales, but they're also expensive. And you do have, I say true, but it's model physics, it's discretized, and there's obviously issues in things like the mixed layer, turbulent regions. For practicality, the mentality I've been working with is how to augment existing platforms. Given that we have altimetry and given that we have Argo, where should we really focus our effort? But are these platforms at risk, and are we not accounting for emerging platforms? So we need to keep in our changing landscape. Because I finished a little early, I might as well show a movie. People like movies. This has nothing to do with the talk. This is if you only have iron on your continental shelf in this model we run, where does it go? And you can see it coming off the shelves and projecting all through the interior. When you hit regions of deep mixed layer, it gets eaten up. This is at 105 kilometers, so you can kind of almost map out where the deep mixed layers are going to be by the remaining blue. But you see, this is one of the big stories here, although coming off. And then I'll play it one more time for the people.
Is it at the surface or in a certain depth or what?
It's so we have a flux of iron on the basically when you touch land, and then the model just
But is it an integrated value to the water column or what?
Oh no, it's just at 105 meters. It's just concentration.
5 meters.
Yeah, and basically, you know, you can watch it coming for the people heading to Heard Island. You can really watch it coming off the Kerguelen Shelf.
So in that area, why is there, there's actually more redness from all the way from South America, so rather than local?
Yeah,
Why do you get that?
I don't know if this is realistic, but it's pretty.
There's no removal occur in the model.
There is removal through biological uptake, but it's 105 kilometers. So I mean meters. Oh, I'm sorry, 105 meters. That K is wrong. There's not that much uptake at this depth. I'll show one more movie. This is oxygen at 105 meters. And you get to see all the ventilation at the continental shelf when it starts to. So this is the model that I used to get the variance statistics that I was able to then say, all right, if you wanted to reproduce this model state, where would you need to measure? Okay, that's yes, go ahead.
You raised the question of the accuracy of the particular measurement.
Yes.
So in the correlations that you showed and the examples you showed, had you sort of scaled them by the a priori measurement error?
I scaled them all by the standard deviation of the model itself, but it's a very small percentage of it. It was down to, it's probably, 0.01% of the standard. It's basically the measurement error was very, very small.
I see. So if we relax back to the low standard, say, which is 1% on nutrients and whatever it was, a millidegree on temperature, how would those pictures change?
It would change. It would change a lot. If one measurement, right now, when we have one measurement, all of a sudden becomes blue. You know perfectly in that area, and that projects out. If you don't have such a small, it doesn't go blue. And so if that one region is correlated with another region, now you have two measurements that correlate. Now maybe it goes blue, but just one might not be enough in your mode of variability. So the signal to noise, I chose the measurement accuracy precision to be very, very high. But yeah, I mean you can easily.
Not high at the surface, for instance, you've got lots of internal variability. You're not simulating per se, right? But
Well,
it's anisotropic depth and so on. So
well, I scaled it.
That picture would change. Actually, if you really included the real errors, that's what I'm putting the guidance on.
Right. It would be good to try, especially I chose the standard deviation to be, a percentage of standard deviation for each variable. I treated them all equally in terms of that.
I see. They're all relatively equally weighted.
Yeah. So if you have let's say the error was 1% of the standard deviation, which is actually smaller than that. That would be 1% of the standard deviation. Oxygen was the measurement uncertainty in oxygen. 1% of the standard deviation in nitrate was the assumed measurement accuracy in nitrate. So yeah, we can make this far more realistic, and I was being simple basically.
So the other piece of information was that you measure 6 variables but reduce the resolution by half. You still have more information actually.
You did better, yeah.
Measured one. So
Well, if you measured just SSH but increased it by 10 times, you did even better.
Yeah, right. Yeah, so
space and time here. So when we look at these maps, we should think of that as if we made a measurement at one instant on a 5-degree grid. This is how those spatial correlation scales would imply that we would get those other variables at that time.
Yes, I've frozen time.
And so it doesn't say anything about temporal resolution of measurement
Right.
or ability to get temporal.
And that's pretty easy to add into the framework, but every time you do, you multiply the dimension of your problem. You've gone from n dimension to n squared dimension. And so people don't usually do objective mapping in that way, just because of computational cost. What you can do, though, is I'm blanking on the name of it, but basically you can say that x at time 1 is some function of x at time 0, and that function is a translator. I think they call it translator. Basically projects you to the next step, and then you shrink your dimension because you're just adding another set of correlation. And so that kind of autoaggressive 1 statistics is really what's done in the Kalman filter, where basically you use the model to just project your thing one step forward each time. So what would happen is, let's see, you have to come back to. I won't try to do it on the fly, but yes, you can. Yeah, to add the time dimension is not at all mathematically complicated, but it does really make it harder to. This h times p hat times h transpose, that my Munson C and Bellinghausen C was chosen because this is as large as my computer could handle the matrix, and I would love to have added in the raw C, but I couldn't do that. I could have taken 6 variables and made it 3 and then added 1 more time dimension, and I probably would have been able to still invert it. Go ahead, Anne.
I'm also a bit tired, but it seems wonderful, these results, I think, and very, very useful. I wonder, well, this is kind of assuming this is in the modern world, so to say.
The modern world.
Modern.
Yeah. Well, the projection, the correlation scales are given by the model, and so yes, it's completely dependent on model resolution.
Yeah. So, the certainty, how we map that into reality, so to say, if you know there's a certain uncertainty in the model, or
Right.
like if you have incorrect.
Well, the model is representing Navier-Stokes, which we believe is the truth, but it's discretized it and it's smoothed it because it's 1/3 of a degree. I would assume if you got to high enough resolution, and we can test this, you would start to actually have the real space-time correlations. What I would recommend doing, though, is not necessarily trying to force us to get all the scales in there, because some of the Eddy scales we might not actually be interested in, but to take the model when we do have, so here we're talking about spatial correlations only, when we do have a repeat hydrography line, and look at the spatial correlation of S, S anomaly along that line, and see how well it does compare to the model. And I think what you'll see is if you do some kind of decomposition, you would see that the model gets all the spatial correlation scales above 50 kilometers or 200 kilometers. There's going to be some scale where the model actually does match the observations, and there's some scale where it doesn't. And that can come into your prior error, or that could just be something you say, all right, I'm designing my observing system. I only want to get scales more than 50 kilometers, so I'm happy with the model the way it is. But yeah, it is important to validate it to figure out what we're not including.
It's not only resolution. There are some errors that in the boundary conditions, like Salinity, and they are more or less known, I think.
Yes,
errors,
but
how large the errors are. So can you use mean?
Well, I mean, we're talking about the model statistics here, so we don't care about the model mean state. We can take out the model drifts even in the isopignal volume budget. We're only worried about the model statistics, and so given that many of these statistics are instigated by intrinsic ocean variability, I think we do capture much of the statistics with today's models. You might wonder, how it depends on, well, if I had 3-hour wind sampling versus 1 day when, you do want to look at the driving inputs. But especially in the Southern Ocean, the intrinsic variability of the ocean is pretty dominant. So for better or worse. For me, it's worse, but I think we do excite most of the statistical scales, and our limit is just model representation or smoothness because of our parameterizations.
I think yes, I think
Yeah. Now there is, the submesoscale does introduce a lot of chaos that we don't have that introduction. So you look at the eddy tracks in the models, and they're much more, they don't go as crazy as they do in the real world. But there is that. Yes.
Isn't this sort of problem that the lowest scale of model that is able to give out is probably 7 times the scale?
Right.
And the amount of variability that you get to the measurement, which is made at,
Yeah.
areas where meter is down. Then how do you bring that in?
Right. So really, this R I'm talking about is the measurement uncertainty. It really is a combination of the measurement uncertainty plus the representation uncertainty of your model. It really, your precision on your instrument might be quite small, but your model doesn't resolve all these internal waves and things that are causing causing variability. And so, yeah, if you're designing your observation system for a 100-kilometer scale, and you're choosing your mapping uncertainty for 100-kilometer scale, then that sub-100-kilometer scale variance is noise in your observation, and you do have to you should add that in. It gets to Nathan's issue, and it does reduce the value of each point measurement, unfortunately. Yeah.
So I'm writing a BAMS article for the state of the environment, and seeing the new results that have been collected in the program. We use this to vary it from last year's results, which come from this analysis, to actually talk about the real differences, temporal differences.
Okay.
And that's so we can be sure that the difference we see 2015 is really true 2014. How would you do that here?
Well, I think to find out if it's really different, you can just look at the temporal decorrelation scales and see if it's really different. To find out if it's significant, I think you need to look at kind of the natural variability. And I don't know if this is, I have to think about that. I don't have an answer.
You're writing one, aren't you?
Well, 1,000 words, what can you say?
I guess the EOFs here are defined from the relatively high resolution model. And then we're projecting the data onto those EOFs that contain all this structure. We have to define the EOFs using data.
Yeah.
We'd end up with quite different EOFs.
Yes. Well, if you wanted, you wouldn't even use, I wouldn't even use the EOFs. I would just use traditional objective mapping there, where you have, you would define, yeah. Sorry.
That's what I'm getting at is that the conclusion that we get so much from SSH is partly because we've included all this information about covariance on scales that we are unable to observe. And so in practice to exploit that covariance, which probably does exist, I guess it gets more difficult if we are not confident that we can use if the model EOFs are
Correct. Yeah. I think we can test them with things like from altimetry to see if these do project well. There's a lot of caveats to these kind of methods. If you don't use enough EOFs, you only use like 2 EOFs. It doesn't take much to know everything, and that's just bad statistics. It's just you need to make sure that you have enough degrees of freedom, and so it's much easier to do all this in EOF space, because now I have 50 EOFs as opposed to the model state, which I sampled every month, and so it's quite a long. you can get into all sorts of troubles if your EOFs are claiming some variance that isn't real. And yeah, people talk about locality and how to deal with that. There are more advanced methods. I would say the biggest issue though is just yeah, you should validate that these EOFs are projecting onto something that we actually see in measurement platform. And two, that you got to make sure that you really have enough EOFs. You can't do this with 3 because you will think you know everything very quickly. If you say the whole system varies as a sine wave, and then you have 1 measurement, well, you're done. So there's a lot of ways to get in trouble.
But I see the strength of this filter is that it sounds very cheap compared to Kalman filter.
It's
and
cheap.
Cordova. So you could basically apply it on models and statistics and see how stable
Right. So I think we're hoping to do this in some different, but yeah, have model intercomparisons where you basically focus on the statistics, focus on what are the modes of variance, what do they look like, how would one project on another. If we use these same EOFs, we did all this and we sampled another model, would we be capturing the variance in the same way? It's because we've simplified the problem down to just 50 EOFs, or it's much easier to validate as well. I mean, it's simpler to do the mapping and it's simpler to validate. So it's a cheaper, quicker method and it would be nice to add at least 1 space, temporal, one, summa autoregressive 1 or 2.
You showed us one little domain that you do this on. If you look at another one, you get a quite different set of views.
So I mean, I have done the EOS for the whole domain. This is EOF 1. I think you would find that the way oxygen and nitrate varies, for example, would be, maybe you have some kind of resonant time in one area and it's more orthogonal in another area. I think there are different dynamical regimes will have different modes of variability and different correlations between temperature and oxygen, for example. And I think even going down in depth, you would find, because when I look at temperature and salinity, the variance almost always just drops with depth. But when I look at things like oxygen, sometimes you find peaks in variance below the surface. And so there's definitely different behavior going on between these variables. And I think that's going to lead to regional variation in how these things behave.
I guess that needs a lot more validation effort.
Yeah.
Step 1.
Yeah, I mean, I really think of this as just a hypothesis, and it definitely needs to be tested, but it does give an idea of where we think we can evolve the system, but at least it gives us an idea of how much value we have from one measurement and where there's big holes based on our existing observation system.
Thanks, Rob.
Thank you.
I believe there's